Good afternoon, everybody. Let's get started. For announcements, exam grading is in progress. I'm going to get those exams graded and back to you, that feedback back to you this week. Also see the class schedule for the assignments coming up. So there's a pre-lab due this week, and the next homework is actually due next week. So homework 4 is due next week. You'll also have a lab this Friday, so that's on the schedule. If you take a look at that, my office hours will be right after class if you want to chat about anything. So stop by, and the TA office hours are posted as well if you'd like to speak with them. Okay, so last time we started talking about first order circuits, and I mentioned that circuits with only resistors, like we've been working with up to this point, well, resistors and sources and switches sometimes. When a source is turned on or turned off, or a switch position changes, the voltages and currents in the circuit change instantaneously from one value to another. They have these step changes. When you add capacitors and or inductors to those circuits, some of the voltages and currents throughout the circuit do not change instantaneously, and you get what we call a transient response. The transient response is the time varying change of voltage or change of current that results from the sudden change. Okay, so there's some sudden change. You turn on a source, you flip a switch, you pull out a resistor, you insert a resistor, something like that. And then you're going to get, for some of these voltages and currents in the circuit, you're going to get this time varying change that isn't a step function. It isn't instantaneous. And I mentioned that when you have resistors, inductors, and capacitors in a circuit, you get, for some of the voltages and currents, this second order differential equation that describes that change of voltage or current. Okay, so you can see this is we have a second derivative, a first derivative, and then the function itself of the voltage equals some constant. If you write KVL equations, KCL equations to find the voltage in this case, you're going to wind up with a second order differential equation. If you restrict your circuit to having resistors and capacitors, or resistors and inductors, then you're going to see that your transient responses are described by a first order differential equation. Okay, here's a first derivative. The voltage function itself equals a constant. So this is going to be the form of the equation for a first order circuit. So if you see a circuit with resistors and capacitors, or resistors and inductors, you're going to have a first order circuit in general. If you have R's, L's, and C's, you're going to have a second order circuit. We're going to concentrate on first order circuits in this class because there are actually some useful things you can do with these first order circuits, as you'll see in class and lab. Okay, so what I'm going to show you are two ways of solving first order circuits. Okay, so I'm going to give you these two approaches to solve these circuits. So the first approach I call the general approach. This is where you analyze the circuit, you write some equations like we've been doing for all of our circuits, and then you solve the resulting differential equation. Okay, I think you're going to see that all of the equations that you derive for a circuit have a common form. And so what I'm going to show you related to that is another approach to solve for voltages and currents, and that's what I call the initial and final value approach. And this is where you perform steady state analysis. We're going to talk about that. And then you determine the time constant. We're going to talk about that. And then from the form of the solution, you're going to see that you can put these steady state values and time constant values into an equation and solve for the transient response. Okay, so I'm going to show you first the general approach, and then I'm going to talk about steady state, and then talk about the initial / final value approach. All right, okay. So let's switch over to the whiteboard. And then I'm going to show you an example here. Okay, so let's start this discussion of first order circuits using an example of an RC circuit. Okay. Okay, so here's the circuit. I take a voltage source and I connect that voltage source to a switch. And then I connect a resistor and a capacitor. So I have R and I have C and I have VS. Let's suppose that I know this value VS. It could be 5 volts or 10 volts, right? You know that value there. Let's suppose I know the resistor and the capacitor values. This might be 100 ohms and 30 microfarads, right? Just making those up. And what I'm going to do is, at some point, after I just build this circuit, I'm going to connect it all together with the switch open. And at some point at time t equals 0, I'm going to close that switch at time 0. Right? And then let's suppose that I would like to find the voltage across the capacitor, VC of t. But before we get into the equations, let's talk about what is going to happen here. Let's suppose I pull this capacitor out of a parts box and it is initially uncharged. So you can charge up a capacitor, you can pull it out of a circuit, it'll maintain a charge. But let's assume that the capacitor that I insert into the circuit is initially uncharged. And then I connect the resistor, I connect this voltage source, turn it on, I leave the switch open. Okay, so you're starting with a capacitor that is uncharged, and that means it has 0 volts across it. Remember, Q is equal to C times V when we talked about the capacitor. The charge on the capacitor is the capacitance times the voltage. So if the charge stored is 0, then the voltage is 0 across that capacitor. Okay. And so we have 0 volts across this capacitor, and we have some voltage, a DC voltage across the source. So as soon as I close the switch, I have a voltage across the resistor. And Ohm's law says if I have a voltage across a resistor, current is going to flow. So current, this closed switch here, right? Current is going to flow through that closed switch, through the resistor, and then charge will be stored in this capacitor. And as charge is stored in that capacitor, right, Q is equal to C times V, the voltage is going to rise. So the more charge that is stored, the higher this voltage gets. Well, eventually, you would think, right, this capacitor is going to keep charging, the voltage is going to keep going up, but at some point, when the voltage, if we could reach the voltage of the capacitor equal to the voltage of the source, or very close to that, right, you're going to have little or no current going through that resistor, right? If the voltages are equal, the voltage of the source and the capacitor, then the resistor has 0 volts across it, no current flows, the capacitor stops charging. But that's what we should see here. When we write these equations, we should see we're going to close the switch, current is going to flow, the capacitor will start charging, its voltage starts rising, and as it rises, the current should fall through the resistor. And eventually, right, we let enough time go by, the capacitor voltage and the source voltage should be equal or approximately equal, as we'll see. It'll approach being equal. Okay. So here's how we're going to do this. We're going to solve for this voltage over 2 different time periods. One, before the switch is closed, and then the time period after t equals 0, after the switch is closed. Okay. So for t less than 0, well, we talked about that. The capacitor is uncharged. The switch is open, the capacitor is uncharged. So we know that versus time, the capacitor has 0 volts across it because there's no charge stored in it while that switch is open before t equals 0. Okay. So then the interesting part comes after the switch closes. And then we have to find some way to write an equation that describes Vc of t. And we know from that last slide I showed you, or 2 slides ago, that we should get a first order differential equation that represents Vc of t. Okay, so it's going to involve a derivative here. All right, so let's do this. There are a couple ways at least you can solve this for this voltage and write an equation. One way is the way that jumped out to me is if I could only define a node voltage up here, and then I know this node voltage over here, if I could say that's Vs, then I can write some equation that describes current through the resistor. So let me do this first. Let me say I'm going to define the bottom node to be a ground node, the reference node. And that means that I can call the node voltage of this node Vc of t, right? Vc of t is the voltage between this node and ground. That's what we have defined here in blue. Okay. And then, so if I, let's solve for t greater than or equal to 0. So this switch is closed now. That means that the node voltage here on this side of the resistor is Vs. It's a DC value, right? Between this node up at the top and this node at the bottom is Vs. And so now I'm going to try to write an equation that describes Vc of t in terms of the other known variables here. So I'm going to do this. I'm going to write a KCL equation that sums the current leaving this node, the current leaving to the left and the current leaving going down here. Let's call this current I1 of t. That says I1 of t. Let's call this current I2 of t. Put a 2 in there. Okay, that's I2 of t. And I can sum the currents leaving that node, set that sum equal to 0. Okay, so I1 of t can be described like this. It is the current going from the node voltage Vc of t to the node voltage Vs. And we did that. We wrote equations like this when we performed node voltage analysis. So I1 of t equals this node voltage minus this node voltage over the resistance. So that is what? Vc of t minus Vs over R. All right, so that's the current leaving to the left. The current going down through the capacitor. Well, we when we first started talking about capacitors, we talked about how do you relate voltage across a capacitor to current flowing into the capacitor, as shown here. Okay, remember, charge is being stored. It's apparently going through the capacitor, but it's really charge being stored in the capacitor. Okay, so I2 is C dV dt. That's from the definition, not the definition, the derivation of current versus voltage for a capacitor. And then by KCL, we can say that the sum of currents leaving that node, I1 plus I2 equals 0. And so let's try to write this equation. Now I want to write some equation that has VC of t, that function, in an equation that we can solve. So let's do that. So I1 of t is VC of t over R, minus Vs over R plus C dV dt, right? I1 plus I2 equals 0. Okay. And so I can rearrange this. I can multiply through by R. Right? If I multiply through by R, I get an RC in front of dVC dt, and I get, well, R cancels out for VC of t and minus Vs. So I can rearrange this equation after multiplying through by R and make it look a little more like a standard differential equation form. Okay, so that's RC dVC dt plus VC of t equals Vs. So there is my first order differential equation that describes VC of t. R is known, C is known, Vs is known, right? This is just a value like 5 volts, 100 ohms, 30 microfarads, something like that. And then we have to solve for that function VC of t. So this is a first order differential equation solving problem here. Okay, different ways you can do this. I'm going to take you down a path that relates to the electrical example here. Okay, you'll see when I solve for the constants in the solution, you'll see how it relates to the circuit. So the first step is this. Let me recognize that the solution to a first order differential equation that has this form always looks like this. The function VC of t, right, the function you're solving for here, is equal to this. It'll always have this form, K1, some constant, plus K2, some other constant, times e to the s, that's some other constant, times t. Okay, so that's the form of the solution. If I have any first order differential equation that is a number times dv dt plus a number, in this case 1, times v of t equals some constant, the form of that solution, the form of vc of t will always look like this. It'll look like vc of t equals some number plus some number times e to the power of some number times t. So we have to solve for those numbers. We have to solve for K1, K2, and S. All right. Okay, so let's do that. Let's do this. I'm going to plug in this form, K1 plus K2 e to the st, this solution, into the differential equation that we derived for this circuit. Okay, and then we're going to solve for K1, K2, and S. So that should look something like this. I'm going to plug in I'm going to plug in K1 plus K2 e to the st in for VC of t. Okay, so I get this. R times C, the derivative of VC of t. So d dt. Now that VC of t is now K1 plus K2 e to the st. Okay, so that's this term. Now plus VC of t. So plus VC of t, K1 plus K2 e to the st. Okay, so there's that term equals Vs. And I have to somehow solve for K1, K2, and S. Remember that R is known, C is known, Vs is known. And T is just the time variable. Okay. All right, so, well, let's take the derivative here. I get, let's see, the derivative of K1, that's constant, that's 0. The derivative of K2 e to the st is K2s e to the st. Remember those derivative rules. So I get R times C times K2 times S e to the st. Okay, so I've just taken the derivative multiplied by RC plus the remainder K1 plus K2 e to the st equals Vs. Remember, I'm trying to get to the point where I can solve for K1, K2, and S, and then I could just plug those values in here. So here's how I am going to solve for K1, K2, and S. I'm going to rearrange this equation into a form where I have a time varying term plus a constant term equals a constant term. And so just, notionally, right? We have some function, we have some term versus time. I'm going to have some term versus time that is, changing with time. And then I'm going to have another term that is a constant with time. And then on the right-hand side, I'm going to have another term that is a constant with time. Right? And this should bug you. It bugs me. It should bug you too, because you can't actually have something that changes with time, add that to a constant, and get a constant, right? So somehow this has to go away, right? If I add this function to this function, something plus a constant, this would have to change with time. So we have to somehow make this term, we're going to take an approach where this term goes away. That's not an X, I'm like crossing it out. This term we have to make go to 0. So we can get a constant equals a constant, because you can't have a time varying function plus a constant equals a constant. This has to go away. So that's going to be the approach. So keep that in mind. I'm going to erase this, but so I can write here. But I'm going to point out which term varies with time and then the constant terms. Okay. All right. So on the left, let's collect the time varying terms. The time varying term is e to the st, right? I have those two here. So I can write this. I can say, let's see, I'm going to factor out a K2 from both of, like, let me underline these, right? I have this term and this term. They're time varying. I'm going to try to combine those together, factor out a K2. So K2 times RCS, right? Then times e to the st. Here I have just a K2. So let's check if this is right. So the two red underlined terms come from this, K2 times RCS e to the st, and then K2 times 1 e to the st. So I've collected the two red underlined terms here. I'm left with K1 on the left and Vs on the right. So K1 is a constant, Vs is a constant, and this term, this first term here, K2 RCS plus 1 e to the st, this varies with time. There's a t in it. So I have to make this term go away somehow to make this equation make sense. Okay, so how can I do that? Well, one way is to make K2 equal to 0, and another way is to make RCS plus 1 equal to 0. If either one of those subterms here equals 0, that makes this whole thing go away, the whole time varying term go away. Well, it turns out that having K2 equal to 0 doesn't make sense. The reason it doesn't make sense is because if I made K2 go to 0, then the voltage wouldn't change, right? If I make K2 go to 0, then this goes away, and I get VC of t equals K1. We know that doesn't happen in the physical circuit, right? I said you're going to close the switch, the capacitor starts charging, the capacitor voltage changes, it increases. So if I made K2 equal to 0 and I cross that term out because it's now 0, then this says VC of t is a constant. That can't be. We know VC of t is going to change as that capacitor charges. Okay. So we know K2 is not equal to 0 because that wouldn't make sense for the solution. So the other way to make this time varying term go to 0 is to take RCS plus 1 and make that equal to 0 to make this equation make sense. Okay. So now I can say, let's see, make that term equal to 0. RCS plus 1 equals 0 to make that equation make sense. Oop, that's not a C sub S, that's a C big kind of intermediate S there. So RCS plus 1 equals 0. And remember, R is known, C is known, S is one of those unknowns we're trying to solve for. So S is equal to minus 1 over RC. So if I set S equal to minus 1 over RC, this term goes to 0. This equation then makes sense. Okay. So that's an important result here. We've solved for one of the three terms, S, K1, K2. We've solved for one of the three that we need. All right. Okay. So, well, what does that leave us with? If you make this term 0, you get 0 plus K1 equals VS. We can also see that K1 equals VS, and VS is a known value. So there's another term we've solved for here. Right, this went to 0. That gets crossed out. K1 equals VS. VS is a known value, so we've solved for S, and we've solved for K1. Okay. To solve for K2, I'm going to use an initial condition. And that initial condition is right after that switch closes, what is the voltage VC of t? Okay, so right, we're solving for t greater than or equal to 0. So at t equals 0, right after that switch closes, what is VC of t? We're going to use that to solve for K2. Okay. Let's take a look at what that value is. I want to know what is VC of t right after that switch closes. And so let me argue this. Let me show you this. If I know that right before that switch closes, we said VC of t is 0. So right before that switch closes, I'll call that VC of 0 minus. We know that's 0 volts because the capacitor was uncharged when we pulled it out of the box. Okay. And somehow we want to know what is VC right after the switch closes for our starting point, our initial condition. What is that? That's what we're going to use to solve for K2. Well, take a look at this. To get from this point in time to this point in time, if we look at the relationship between current and voltage for a capacitor, and write that down here, I is equal to C, oops, I need my C. I is equal to C dVC dt, right? We have to obey this. So what you could interpret from this equation, understand from this equation, is that VC of t cannot change instantaneously. It can't step from one value to another. Like VC of t can't do something and then step instantaneously straight up and then do something else, or it can't do something and then go down instantaneously, jump to another value and then do something else. It can't do that versus time. Right? This can't happen. Why? Because that would be an infinite or negative infinite derivative. Okay. And I of t would need to be infinity. So what we're saying is that I of t could be big, but it can't be infinite. So VC of t cannot change like a step function. It can't go from one value to another instantaneously. So another way of saying that is at some point in time, and then right after that, you have to have a continuous function. VC of t has to be a continuous function. So if VC right before 0 is 0, then VC right after 0 is 0, or you take the limit as these two approach each other and they're the same value. Okay, this was just a long explanation of this is why we know that right after the switch closes, VC of t is still 0. It cannot change instantaneously, and then it can change smoothly to other values, but it can't have a step change. Okay. All right, so great. What's that let us do? Well, that lets us say that we're going to say VC of 0 equals 0, because right before and right after is 0. So VC of 0 is 0. Well, I can use that. I can say VC of 0 equals, well, K1 plus K2 e to the st. Okay, K1 plus K2 e to the st. And in this case, let's replace t. I'm going to erase this. Let's erase t and say that is 0, because t is equal to 0. Okay, so this equals, well, VC of 0 is 0. This is 1, right? E to the 0 is 1. So I get K1 plus K2 times 1 equals 0. And we figured out what K1 is. K1 is now a known value. So we can solve for K2. In this case, K2 is equal to minus K1. Okay. And that means K2 is equal to, see if I can fit it here. K2 equals minus VS for this particular problem. Okay. All right. So we've solved for K1, K2, and S. We can plug those values back into this general form of the solution here. Okay, so VC of t, back using this here, VC of t equals K1 VS plus K2 minus VS plus negative VS e to the st. E to the S is minus 1 over RC times T. So this is minus T over RC. Okay. So that is for T greater than or equal to 0. So if I want to write the complete solution, if I want to be like strict here, then I would say VC of t equals 0 for t less than 0, and VS minus VS e to the minus t over RC for t greater than or equal to 0. So that's the real answer here. Okay. So someone asks, were we able to set RCS plus 1 to 0 because that term will go to 0 at infinity? No, I set RCS plus 1 equal to 0 because we know K2 cannot be 0. And so we need something else. We need some other way to make this whole term equal to 0, right? We got to make this e to the st. We have to make that go away because you can't have something that changes with time plus a constant equal to a constant, right? If you have something that changes with time and you simply add a constant, then the left-hand side of this equation is still going to change with time. It's going to change with time, and that can't equal a constant, right? You can't have something wiggling with time equal to something that doesn't wiggle with time. So we have to make this term go to 0. The only way we can do that is set RCS plus 1 equal to 0. Okay. All right. So this is the this is that general way I said to the general approach to solving a first order circuit problem. Right. We have a series R and a series C and a voltage VS with a switch. This one configuration that results in this, right? The answer to a different RC circuit, maybe of two resistors or two capacitors, or it's switch in a different place, maybe you're pulling a resistor out, that would be a different circuit. And you'd have to write different equations and you'd wind up with a different differential equation that describes the voltage. The general form is still going to be the same. Your solution for this first order differential equation is still going to be K1 plus K2 e to the st. And then you'd have to plug that solution into whatever your circuit's specific equation is, and then do the same approach. This same approach will work. You can set the equation, form the equation into terms where you have a time varying function plus a constant equals a constant, find some way to get that to go to 0, solve for S, solve for K1, and then use the initial condition to solve for K2. Okay, so that works, but you need to write this specific, right? This, what we did here, that's for this circuit. So this is specific to this circuit. This is general. That approach is general for other circuits. Okay. All right. So if you want to talk about, especially why do these terms go to 0? Why do I have to make that term go to 0? Or why is this the general solution? Well, it is, because see that every first order differential equation that looks like this and has a constant on the right, its form of the solution will be that. But you use that to solve for the specific transient response. Okay. Okay. Someone says, can you take the derivative? Can you also take, I think, the derivative dt of both sides? Well, stop by after class. I'm interested in what you're thinking there, because then I'd wind up with a second derivative. I'd have a second derivative plus a first derivative equals 0. So you have a way to do that. The reason I like this approach is because it relies on the understanding that, for example, we have an uncharged capacitor, so that you can solve for the initial condition here, and that K2 cannot be 0 because you know that VC of t is going to change. Okay. Yeah, lots to talk about here. So yeah, if you have different values, maybe two capacitors, maybe a resistor, maybe there's a parallel resistor that gets switched in or out, then you're going to have different values. compared to what we have here. So just have to work through the problem. But let me start talking about the, let's see. Let me summarize what we did here, and then I want to start talking about time constants and steady state. Okay, so let me bring up the slides again. Okay, so this is what I'm calling the general approach to solving a first order circuit, right? So you use any circuit analysis approach, KVL, KCL, maybe you can use some voltage division or node voltage analysis, whatever you're doing, to write a first order differential equation describing whatever you're looking for, a voltage or a current. And so you're going to get an equation of this form, some number times dv dt plus some number, it could be 1 times v of t equals d, some number, some constant. And then you're going to substitute k1 plus k2 e to the st into your first order differential equation for that circuit. Substitute that in for either vc of t, or this could be a current too. This could be I of t, di dt, or I of t here. And then you're going to rearrange the equation to have a time varying term that will drop out of the equation, right? This term must go to 0. So you get a constant equals a constant, and then you can solve for s. And then you can use solve for k1 using the remaining terms of the equation, and solve for k2 using the initial condition, right? So this switch closed at t equals 0. So if you have, switch closes at t equals 1 second, then that's your time for the initial condition. All right, so that is what we just went through. And I think, right, that's a reasonable way of solving these problems. I'm going to show you another way though. Someone asks in the chat, so you substitute anything that is of t with k1 plus k2 e to the st. That's right. So if you had, if you're solving for a current, like I of t, right, you would say I of t equals k1 plus k2 e to the st, and then you would solve for that current. So that's right. Okay. All right. But before I introduce you to steady state and time constants, let's do this. Let's do a clicker problem. So grab your clicker apps. And we start the clicker up here. Which one of these is a first order circuit? A first order circuit has an L and an R, or a C and an R, but not both. So here, this is an RLC circuit. This is a second order circuit. You would wind up, if you solved for voltage across the capacitor, you'd wind up with a second order differential equation. Because remember how we had a derivative here in the expression for current. Well, here you would have an integral. So you'd have an integral, a derivative, and a variable, maybe doing a KVL equation or something, or a KCL equation. You would wind up with a second order differential equation. Let's see, over here, well, we only have a capacitor. So that would probably be a first order circuit. Here we have capacitor and inductor, second order circuit. Here, capacitor and inductor and resistor, second order circuit. So these are all second order circuits, A, C, and D. So you'd have B as the first order circuit. Let's take a look at this transient response. So in general, this is what you're going to see. You're going to see when a sudden change happens in the circuit, a switch is thrown, a resistor is pulled out, a resistor is inserted, something happens like that. You're going to see a starting point, an initial value, and then you're going to see this exponential change, right? E to the minus 1 over t times something, right? You're going to see this exponential change. And then you're going to see sort of a convergence to another constant value. So there's a starting value, there's this exponential change, and then there's this convergence to another value. So right here, this is the transient response where the voltage or the current changes from one value to another value and then sort of, becomes constant, becomes steady again. So how do you determine that, right? Is this really steady here, or I see a little kind of it looks like it's still rising. Is it still rising, right? You can't tell. And actually, if you look at the exponential, yes, it's always changing just a little bit. But in engineering, we're going to say, well, when has that value converged after its transient response? When has the value converged to within 99% or within 1% of its final value? In other words, it's 99% of the way there. It's within 1% of its final value. Okay. When has that, for all practical purposes, that value become steady? We're going to call that state of being steady. We're going to call that steady state. And so what you're going to see is that the voltages and the currents in first order circuits, the ones that change, will have this exponential term, e to the minus t over something. We're going to call that something tau. And that tau is the time constant. We're always going to have an exponential of this form. Tau is the time constant. It is in units of seconds, right? The argument of an exponential has to be unitless. So seconds over seconds gives you a unitless value here. So tau is in units of seconds, and it characterizes the response time. It characterizes how long does it take between the sudden change and when we've become steady, when the voltages and currents that were changing now are at a constant value roughly again. And so at 5 time constants, you'll see that the voltage or the current is actually within 1% of reaching its final value. And you can see this right here, that when t equals 5 tau, right? So to make t equal 5 tau, you have e to the minus 5 tau over tau. That's e to the minus 5. That's 0.7%. That's within 1%. Okay. So we've converged to within 1%. So we say that after 5 time constants, the circuit has reached steady state. So that's how we're going to define when steady state happens, is after 5 time constants, because we're about 1%, we're 99% of the way there. Okay, so someone asks, so tau is equal to minus 1 over s from the previous example. That's exactly right. So you're going to see if you equate e to the st, equate that to e to the minus t over tau, then tau is equal to minus 1 over s. So if you've solved for s, you can get the time constant. Okay. And you don't have to have these rising voltages or currents. You can also have falling voltages or currents. They can start at one value and then fall, but the concept is the same. You have an initial value. That's when the sudden change happens. You get this exponential change. You converge to another value. The transient response is during that changing voltage or current, and the steady state happens after 5 tau when you're 99% of the way there. Okay? All right. So we'll continue this next time. But for now, in closing, look for your exam grades this week. I will send out an announcement when those are all done. They're going to take me a little while longer. I'm working through those. Check out the pre-lab that is due this week. You'll have a lab this week, and look at the other assignments coming up. I don't think there's any quiz due this week, so those were mostly at the beginning of the class for the basic material. So I will start office hours in just a few seconds. If you would like to join, please join. If not, I'll see you next time. Have a great night.